Okay. Hello everyone, my name is Rafael Constantinou, and I work as a senior full-stack developer at CYRIC, which stands for Cyprus Research and Innovation Center, and which is located in sunny Cyprus. I'm here today to present to you the BEMServer, which is an open source platform for building energy performance management. Before moving on, allow me to say that this paper comes as a direct outcome of the many published papers under the Horizon 2020 project, which is called Hit to Gap, that mainly deals with reducing the gap between the theoretical energy performance of buildings and the actual consumption in use by focusing on what happens and on what could be done while a building is in operation. So at first I would first attempt to give you the energy management in buildings by providing you with some context and challenges. I will then describe what the BEMServer does and in detail the data model that we have used along with its accompanying functionalities. And I will then present the BEMServer in the Hit2Gap project, and at last some conclusions. So as my previous let's say colleagues have mentioned, buildings, the energy and buildings is a key challenge in our modern society, as buildings and their usage have a huge environmental impact. There is an estimate of 40% of the energy consumption nowadays is being derived by an immediate need of buildings that require energy, and this results in around 30% of CO2 emissions. So the energy consumption and on how to let's say reduce this energy demand. Nowadays, there is not an immediate solution that can solve this issue, because there are many involvement of many actors. We have different level of actors, and each and everyone has a different expertise. Some of these actors are energy facility managers, building owners. So we have to let them know on what their data are. And we need to find a way for us to give them insight on what the actual data are saying to them. So we have buildings, usage, and occupants which are different. So this is why we need different solutions. So what we currently have are many BMS systems that are practically very old. They are built on a monolithic solution. They are not flexible enough. The configuration of them is kind of obsolete. So there is a huge difficulty into emerging and transforming the traditional BMS system into the modern new era. So as buildings are becoming more and more complex, we need to find a way for different experts and the energy module developers to come together so that all of them can use the underlying data and start building data integration modules so that data are having a more sense. So what we end up is buildings are now more and more monitored, but at the end of the day, having a lot of data does not mean that we're actually in a position to extract knowledge and information, because all these actors are now starting to get some difficulties to point to the correct information in order for them to be able to analyze the data that we have. And this arises from the fact that we're actually mainly dealing with heterogeneous data. We're actually dealing with data coming from sensors, from HVAC systems, and so on and so on and so forth. So this is where the BEMServer comes in. There is a need to create an open and modular and extendable EM solution. The openness is guaranteed by making the data easily available so that new module developers can deploy their services, can absorb data, in contrast with the traditional BMS systems which are now closed and are acting like black boxes. So we have done this using standard RESTful APIs, and by maintaining that there is a data abstraction by actually structuring the underlying heterogeneous data. So instead of having monolithic solution, we kind of transform the existing monolithic approaches into the new era, let's say, and we made it open source so that this BEM server cannot be easily maintainable and deployed by any IT expert while maintaining that the system is secure. And I'm going to briefly outline how the security is persisted. Now, as you can see in this diagram, on the left part, we have the traditional buildings with their existing BMS systems. So currently, the buildings are pushing data into their, let's say, in-house databases. So this is where, so on the red triangle, on the red rectangle, this is where the BEM server comes in. By only using a simple connector that an IT administrator can install on a traditional, let's say, BMS system, data can now start being pushed into the BEM server core for analysis, blank detection, correction, and then the data are being exposed to the outer world with a BMS server API, allowing third-party modules that are not physically implemented inside the BEM server, but are hosted in a modules developer environment to start obtaining data. And I'm going to explain at next. So this is the BEM Service Architecture. I will try to explain from the bottom up what the basic architecture is. So initially we have the field level where the data are being pushed to the ETL level, which stands for extract, transformation, and load. We have the storage level, the orchestration, and the application. In detail, the field level is our sensor data, which are the building data, in which I have already mentioned that this is the heterogeneous data that causes the mess. So we have sensor data coming from window sensors, PV meters, HVAC systems, parking sensors, whatever you can think of, and it is attached on a BMS system. So all these data are heterogeneous, and all these data are being pushed to the ETL level. So as soon as the data are being coded into the ETL level, we have deployed several conversion algorithms that ensure that all data stored in our database are stored in a uniform order. So for example, a temperature, all temperature sensors are now stored into, I don't know, degree Celsius. We have also deployed several blank detection and correction algorithms that enable us to quickly identify sensors that are not operated as they're supposed to be. So this creates events and alarms that are then sent to the IT administration or the facility managers to go and fix those sensors. And we have also used and deployed outliers detection and correction algorithms that enable us to quickly resolve any sensors that are producing malformed data or are producing data that are not within the correct bounds. As all of us understand, the ETL level is a very let's say, an iterative process, and we are constantly working on improving the intel level, because different sensors creates different demands. So for us, this is a very crucial part on how we're actually transforming the data to be pushed back to the module developers that are going to consume the data afterwards. So we're then moving up to the storage level. We have used, for the different types of data that we currently have, we have used different storage systems. For example, for our time series database data, we are using the time series database, which is the HDF5. For all the generated events, we are using the traditional relational database, which is the SQLite. And for the metadata, which is the semantic data storage, we have used the Apache Jena. So all these technical choices remain transparent to final users, and we want to make it this way for everyone to be easier to use. Of course, this is easily changed since our solution is open source, but we have used these kind of technologies because of our expertise, and because we believe that this is the best solution for each of the data type explained before, since this solution provides us with better time response, better robustness, and flexibility. And last but not least, we have to mention the semantic data model. We have used the IFC to transform built-in descriptions, but this didn't help us to specify sensor metadata. So this is why we have used the SOSA. But again, because we needed to find a way to bring together the IFC for the buildings and the SOSA for the sensor, we have also used the haystack. So this is where the heat-to-gap ontology comes in, which is the adaptation of the haystack ontology as a glue between the IFC and the SOSA. And then that's the final and best part, which is the presentation of data, or as we called it, the orchestration level. So at the end of the day, the data remains useless unless we give the data to the module developers, to developers out there that have the expertise, that are data scientists, that are facility managers, and we want to give them insight on what their BMS is all about. So this is why we have created a RESTful API with a very powerful online documentation that enable users to easily get access to the data, perform resampling, unit conversion, and perform simple arithmetics. And all this is done using the necessary security, which is the SSL. We also provide role-based access to the registered users on the platform, and we have also deployed a SAML certificate functionality in order for modules consuming data to be able to push back events. So in our case, our module, because I'm a module developer, for this kind of project, we're actually consuming data from an existing building management system in France. I don't know if you know it. It's called the Challenger building. So what we do is that we are actually consuming PV meters data. We are performing monthly simulations, and then using the SAML and certificate authentication, we are actually pushing back data into the platform, and other modules can then take those events and visualize them in our own visualization modules. So as I have already mentioned, the BEMServer is actually currently deployed within the Heat2Gap project. We have a single instance being deployed on the cloud. It covers the 4 main pilot sites, which is the Challenger, which is located in Paris, the Nanaguno, which is located in Spain, the Villanov, which is located in Poland, and the Newark, which is located in Ireland. And we have provided one single entry point for each of the developer modules to use. Finally, some conclusion. We perceive that the BEMServer is a good support for open, modular, and extendable BEM solution. It is tested in real conditions, and what we need to do as further improvement is to better describe the HVAC system, is to enable direct communication possibilities with proprietary protocols, to better deploy RESTful APIs, and to enhance the pre-processing ETL level that I have already mentioned, and to develop more services as of attracting more and more module developers to come into the platform, register and start consuming data. So that will be all from me. Thank you for listening to me. If you have any questions, I will be more than happy to